Hi, I'm Kashish, and today I'm going to explain homework 9 problem 2. So the question is that we've been given n as a Poisson process with parameter lambda, and the probability that k points arrive between t2 and t1 is e raised to minus lambda t2 minus t1 into lambda t2 minus t1 divided by k factorial, this whole part raised to k. And we've been given a stochastic process x of t, which takes the value 2 when n is odd between 0 and t, and it takes the value minus 2 when n is even between 0 and t. So the first question is that draw a few samples. So this is a sample that I've drawn. And this question is basically similar to the telegraph signal example. So this is how a telegraph signal looks, and this is how a sample when x of t takes the value 2 and minus 2 would look between 0 and t when n is odd and n is even. So that's the first part. The second part is find the probability that x of t is equal to 2. X of t is equal to 2 is basically that n takes odd values between 0 to t, and therefore we deduce that k, so n takes odd values between 0 to t is going to reflect in this process, and that's why we'll know that k should take values 1, 3, 5, so on and so forth. And t2, t1 will basically be, t2 will be t, and t1 will be 0, 0 to t, t1 to t2, so we can easily see that t1 equals 0 and t2 equals t. And once you put those values, so e raised to minus lambda t2 minus t1 or t minus 0 will come out as a common factor into lambda t raised to 1 divided by 1 factorial plus lambda t raised to 3 divided by 3 factorial raised to 5 divided by 5 factorial, 7 divided by 7, so on and so forth. This is basically the expansion of change of lambda t, and change of lambda t can also be written as half of e raised to lambda t minus e raised to minus lambda t. And once you open up the brackets of this, you're going to get probability of x of t is equal to 2 is half of 1 minus e raised to minus 2 lambda t. The second part of the problem, the third part of the problem is that we have to find the mean value e of x of t, that is. So e of x of t is basically the probability of number of even points minus the probability that the number of points are odd. So we already know the probability of number of points are odd, that was p of x of t is equal to 2, which was the b part of this problem. Now we'll find p of x of t is equal to minus 2. So since it's even, the values that will be taken by k are 0, 2, 4, 6, so on and so forth. And once you put in the values, you're going to get something like this, and this is the expansion for cosh of lambda t. Cosh of lambda t can also be written as e raised to lambda t plus e raised to minus lambda t divided by 2. And once you open the brackets, you're going to get half of 1 plus e raised to minus 2 lambda t. And thus the expected value will be the probability that number of points were even minus probability that number of points were odd, and once you open up the bracket, you're going to get e raised to minus 2 lambda t. The fourth part of this problem is that we have to find the autocorrelation function t1, t2. For this, the following observation, which I'm going to explain, is very important. So consider that t1 is greater than t2, and right now we'll be looking at the markings done in blue and the written material that's in blue. So if you consider this point to be t2, that means t2 is minus 2, it's taking a value minus 2, we can see that only one point has occurred. And if you consider t1 to be taking a value plus 2, we can see that 1, 2, 3, 4 points occur between that interval. And 4 minus 1, that's number of points that occur at t1 minus number of points that occurred at t2. 4 minus 1 is 3, which is an odd value. So we basically observe that when x of t2 is equal to minus 2 and x of t1 is equal to 2, we get odd number of points. Or you could even check by taking x of t2 is taking a negative value and x of t1 is taking a positive value. Now we check for a condition where x of t2 and x of t1 will either be 2 or minus 2. So we have shown an example that x of t2 and x of t1 take the values 2 and 2. So when x of t2 is out here taking a value 2, 2 points occur. when x of t1 is out here taking a value 2, 1, 2, 3, 4, 5, 6 points occur. And the difference is 6 minus 2, 4, which is even. So basically when x of t1 and x of t2 take the same value, whether it be minus 2 or 2, even number of points occur. And also keep in mind that minus 2 into minus 2 is equal to 4 and 2 into 2 is equal to 4. So even the multiplication of x of t1 into x of t2 takes the same value. And when x of t1 takes a negative value and x of t2 takes a positive value, or the other way around, we get odd number of points, and 2 into minus 2 is minus 4. So the autocorrelation of t1, t2 is basically expected value of x of t1 into x of t2, which will be x of t1 into x of t2 multiplied by the probability of x of t1 into x of t2. So we're going to take two conditions out here because we have two cases, one in which x of t1 into x of t2 takes a positive value and we get even number of points, and one in which x of t1 and x of t2 take a positive and a negative value, therefore minus 4, and we get odd number of points. So 4 into, now we're going to take x of t1 into x of t2, probability of x of t1 into x of t2 when it's minus 2, you get this. But the only difference will be that here t will take the value t1 minus t2, and out here when x of t2 is equal to 2, t will take the value of t1 minus t2. So that's what you insert out here, and once you open the brackets, you get 4 times e raised to minus 2 lambda t1 minus t2. Now in this case, we assume that t1 is greater than t2. If we did not know t1 is greater than t2, we would definitely know that it's the difference between the two. So that's why the absolute value of t1 minus t2. And the last question is x of t white and stationary? So we can easily say that r of t1, t2 is a function of t1 minus t2, and also that the expected value here, the expected value is a constant. E raised to minus 2 lambda t is basically a constant. And since both the conditions to be WSS are satisfied, we can say that x of t is a White's and stationary signal. Thank you.